everyone, this video is an introduction to section 16.5 on the topics of curl and divergence. So let's start with some big picture of where we're headed. In our last section, we discussed Green's theorem, and Green's theorem sets the stage for the final act in our exploration of calculus. Green's theorem, as you recall, tells us how to relate a double integral over a plane region D to the line integral around the boundary of that region. And our last goal is to lift Green's theorem out of the plane and into space, and this is something called Stokes' theorem. So what we'll do is we'll want to relate a triple integral over a surface to a line integral around the boundary of that surface. But in order to do this, we're going to need some new tools: curl, divergence, and surface integrals. And so in this section in 16.5, we're going to talk about curl and divergence. And we'll get into surface integrals in the next section. So let's start with curl. So if F is a vector field in R3, whose components are P, Q, R, then the curl of F is another vector in R3 whose I component is composed of the partial derivatives Ry minus Qz, the J component, the partial derivatives Pz minus Rx, and whose K component are the partial derivatives Qx minus Py. Now, if you're thinking, oh no, how am I ever going to be able to remember this? I don't blame you. I would also panic the first time I saw this. But there's a trick. So here is a way to help us remember this formula for the curl. So we've still got our vector in R3 for F, our PQR. And we're going to define something called the gradient vector, denoted by this upside down triangle, our gradient. And it's an operator whose components are our partial derivatives. So the I component is the partial derivative with respect to x, the j component is the partial derivative with respect to y, and the k component is the partial derivative with respect to z. And in this case, we can remember our curl of F to simply be the cross product of this gradient operator with F. So we'll create a 3 by 3 matrix whose first row is ijk, whose second row are those partial derivatives from our gradient, so partial derivatives with respect to x, y, and z, and whose third row are the components of F, P, Q, R, and then we'll take the determinant of this 3 by 3 matrix, or the cross product. And so if you remember how this works, then for our I component, so we'll have the partial derivatives R with respect to y minus Q with respect to z. Then we'll have to do a minus for the j component, partial derivatives of r with respect to x minus p with respect to z, and then finally for the k component, partial derivative of q with respect to x, then p with respect to y. And so this will give us a handy way to actually compute the curl. So here's an example. Let's compute the curl of F for the vector field that we see here. So recall our shortcut. The curl of F is the cross product of the gradient operator with F. And so we have as our first row ijk, as our middle row our partial derivatives with respect to x, y, and z, and then as our bottom row the components of F. So the I, J, K components of F. And now we compute the cross product. So for our I component, we start with the partial derivative with respect to y of xyz squared, which gives us xz squared, minus the partial derivative with respect to z of xy squared z, which is xy squared. Great. Then we have a minus for the j component, the partial derivative with respect to x of xyz squared, which is yz squared, minus the partial derivative with respect to z of x squared yz, which is x squared y. Finally, plus for our k component, the partial derivative with respect to x of xy squared z, which is y squared z, minus the partial derivative with respect to y of x squared yz, which is x squared z. And so this vector that you see here, this is the curl of F. Great. Now, as you might have guessed, the curl vector is associated with rotations. That's how it's named. And because it's a vector, we need to understand what the direction and the length of the curl of F is telling us. So if F is a velocity field in fluid flow, then the particles near the point XYZ in the fluid tend to rotate about the axis that points in the direction of the curl of F. And the length of the curl vector is a measure of how quickly the particle moves about the axis. So, in other words, if the curl of F is 0, then that would tell us that a tiny paddle wheel moves with the fluid but doesn't rotate around the axis. The fluid is rotation free. On the other hand, if the curl of F is non-zero, then that would tell us that the paddle wheel is going to rotate about its axis. All right, so that's a brief introduction to the curl. What about the divergence? So thankfully the divergence is easier. Again, we've got our vector field in R3, F is our PQR, and we define the divergence of F to be the partial derivative of P with respect to X plus Q with respect to Y plus R with respect to Z. And if you need a shortcut to remember it, the divergence you can think of as the dot product of our gradient vector with F. So a quick observation here is that the curl is a vector field, but the divergence of F is a scalar field. One the cross product, the other the dot product. Let's do a quick example. Let's compute the divergence of F for this same vector field we had in our previous example. Here's our formula. So for the divergence of F, we want to take the partial derivative with respect to X of our I component, X squared YZ, plus the partial derivative with respect to y of our j component xy squared z, plus the partial derivative with respect to z of our k component xyz squared. And so we get 2xyz plus 2xyz plus 2xyz. So the divergence of F in this example would be 6xyz. Notice again we're getting a number for the divergence, whereas we got a vector for the curl. So let's see how we can understand the divergence. Divergence can also be understood by letting F be the velocity of a fluid or a gas. And if so, then the divergence of F is the net rate of change with respect to time of the mass of the fluid or the gas flowing from the point XYZ per unit volume. In other words, the divergence of F measures the tendency of the fluid to diverge from the point XYZ. So if the divergence is positive, that would tell us that fluid is flowing from a source point, as you see in the picture here. If the divergence is negative, that would tell us that the fluid is flowing toward a sink point. And when the divergence is 0, we would say that the fluid is incompressible. Okay, so this is our brief introduction to the definitions of curl and divergence. We'll look a lot more at these two in class together, and I look forward to seeing you then. Bye, guys.